So, good morning to everyone. The thing which we are discussing in the previous class about the asymptotic notations, and there are three types of asymptotic notations present: big O, big omega, and theta. Theta, big omega, and theta. These three asymptotic notations are present, and I have discussed the big O in the previous class. Today we will discuss about the omega notation and the theta notation. So in this case, for omega notation, the function fn equal to omega of gn. We can say if the functions fn equal to omega of gn and implies that the positive constants of c and n0 such that fn is greater than equal to c of gn for all values of n greater than equal to n0, then we can say it is of omega notation. So if we see with an example that we consider fn equal to 2n plus 3. See, we consider fn equal to 2n plus 3. Now, what will be gn? Now, in this case, we will consider gn as a, here I have in fn function, I have mentioned 2n plus 3. So simple form of mentioning gn is consider the n, omitting the values, coefficient values and the constant values, and only consider the n. So here, that's why 2n plus 3, we omit the coefficient and also the constant and only put n value in the gn. This is the simplest form for considering a gn. If sometimes there is fn functions mentioned, now you have to consider the gn for omega notation. Then you can do like this, that if it is mentioned here, then omit the coefficient and the constant value and only put the n value. So that's why here I have written n. And in case of coefficient, I have mentioned 1. In case of coefficient, I have mentioned 1. That is 1 into n means n. Now, we have to consider it that if for all value of n will be greater than equal to 1. So if we put 1, then it will become 5. 5 is greater than equal to 1. So our value matches. Because we have to choose such a value that becomes that fn becomes greater than equal to c of gn. That's why we choose such a value. And that's reason I have choose gn as a n. And if we consider, if we put the smallest value as a 1, then you can see that is 5 greater than equal to 1. So that means our condition is true. So fn greater than equal to c of gn. We can consider that. So that's how our omega notation works. We can consider our omega notation like that. Clear? For in case of omega notation, we do like this, that we have to if fn function is mentioned, then we consider the gn as like that. And after that, for if our condition is n greater than equal to n0, means for all value of n it will be greater than of n0. So we put smallest value as 1. And after putting the smallest value, we can see that it is our value fn is greater than or equal to c of gn. So we can say our fn is the order of n, because it is gn is n. So fn functions is the order of n. Now, same like that, in the omega notation, I have also done that, the upper order. So if we put n in case of big O notation, that if we put n log n square, we can put such like that. And in case of omega notation, we can also mention this root over n log n 1, because omega notation is the lower bound of any functions. So we can mention n, root over n, log n, 1, all the values we can mention here. But we couldn't able to perform these values, n log n, n square, n cube, 2 to the power n, 3 to the power n, because this is all the upper bound of a functions. And if this is the upper bound of a function, we cannot use this because upper bound of a function is used for the big O notation. And this is the omega notation. So that's why here I have used n. We can also, here I have used n. You can also use like that, log n. In case of n, you can use, here I have mentioned gn as a n, but you can mention also as log n or root over n, which is the lower bound of any functions. So that's why you can see here, first I have written that fn is equal to order of n. Or we can also say, if we use the log n function, then we can say fn is also the order of log n. So during the omega notation, we can mention like that. Okay. And in case of theta notation, we can say if a function is fn equal to theta of gn, that is all value of positive constants c1, c2, and n0. c1 and c2 is the constant, and n0. So n0 is the minimum value. So such that c1 of gn less than equal to fn less than equal to c2 of gn. So because this is the condition, our fn will be greater than, when there is omega notation, our fn will be greater than average. This is the theta notation is used for average condition. So for this, we have to consider both lower bound and upper bound functions both. So in that case, you can see our fn is mentioned, fn c of c1 gn less than equal to fn, and it is less than equal to c2 of gn. That's why this is mentioned like that, because we are considering both. In case of theta notation, it is the average condition. That's why you have to consider the both. So if fn is mentioned as 2n plus 3, so we will consider c1 of gn as n, because it is case the omega notation. So it will be n less than equal to 2n plus 3 less than equal to 5n. So that's how we can consider it, and our fn will become theta of n. Now here we couldn't consider upper bound or lower bound, so only n. In case of theta notation, only we can solve it through n only. We didn't able to consider other functions, like in case of upper bound functions we consider n log n, then n square, and in case of omega notation we consider log n, root n, both we can consider that. But in case of theta notation, we can say that average condition is based on the n value. Average condition n is the average bound. So that's why in case of theta notation, we only able to write fn equal to theta of n. We didn't able to write it theta of log n or theta of n square, because if theta of log n, we cannot write that because it's the lower bound of a function, or theta of n square, we couldn't able to write that also because it is the upper bound of any functions. So that's how theta notation works. Clear?
Yes, sir.
Okay. So this is all about the asymptotic notations. Asymptotic notations about big O, big omega, and theta. Clear? So today I will start another topic. I will share with you with another topic. No, this topic is of a recurrence relation. So today I will discuss another topic, which will be the recurrence relation. Now, first we will know that what is the recurrence relation. Now, this recurrence relation is basically used for recursive function. You can see in case of factorial, recursive calls are used. That how recursion works. Recursion means what? Recursion means a function can call itself. Number of times a function can call itself. And recurrence relation is basically used for recursive function. Now, consider this as an example. Through an example, it will be clear to you how recurrence relation or how recurrence relations can be solved. So consider this. This is a first consider this. This is our algorithm. This is our algorithm. Now you can see this algorithm is written in the simple C format, simple C functions format. Okay, so here you can see that it is written as a void test. Test is the function which is taking input n, which is taking as a one input, that is n. And if n greater than equal to 0, if n value is greater than equal to 0, then it will print the value of n, and again it will be call itself, means after calling it will be here. So that means this functions works like a recursive way. This functions works like a recursive way. If we take some value of n, and then the value of n will be, and the condition will be checked if the value of n is greater than equal to 0. If the value of n is greater than equal to 0, then the value of n will be printed and the recursive call will be performed. This is the total work done by the function. Now, in case of recurrence relation, we can solve it with two ways, either solving the recurrence relation or solving with a tracing tree. We can say it's solved with a tracing tree. Okay, so now we will first see how this will be solved, how this can be solved using tracing tree, and then we can solve it with recurrence relation problem solving scheme. Okay, so first we will see how it can be solved using the tracing tree. Now you can see in the tracing tree, our functions is void test intent. So we are considering that our n value is, we are considering that our n value is 3. We are taking the n value as a 3. So in case of this function, how it will be work? That first test functions will take n as a 3. So test 3, here test 3, our functions are taking the input, it will be 3. And what this functions is doing, this functions is printing the n value and again calling the functions itself. So first, if we trace the tree, then first 3 value will be passed to the function. In case of n, we are considering it as a 3. So the 3 value will be passing in the functions, and the 3 value will be printed, because in the condition this is mentioned, if n greater than equal to 0, then print n and call the functions itself. So our n will be printed and the functions will be called. That's how it works. Because if you see that how it works, that first here 3 value will be, here we can pass 3 value, we can passing 3 value. So that is 3 greater than equal to 0. Okay, 3 greater than equal to 0. Then 3 will be printed, and test 3 minus 1 means test 2. This will be this function's test function will be called again. That is shown here, that if we will pass 3, then the 3 value will be printed and the function will call itself. Then there will be another time this will be run, the functions will be run again, and the value will be, then n value will be 2. So 2 greater than equal to 0. Yes, 2 is greater than equal to 0. So 2 value will be printed and the functions will be called again. Then test 2 minus 1, that will be test 1. So this will be again called. These functions will be again recursively called. So test 1. That's why it is written. After that, the n value now becomes 1. N value now becomes 1. So 1 greater than equal to 0. 1 greater than equal to 0. So n value is greater than equal to 0. Yes. So 1 will be printed. That's why this, you can see 1 is printed here. And again 1 is printed here. So now test functions will have, which Test functions will become how much? Test will be test 1 minus 1. Yes, test 1 minus 1 means test 0. So these functions will be again recursively called. Now, then 0 greater than equal to 0. This is not possible. So if this is not possible, then 0 greater than equal to 0. So it will be run, no, it will not run again. So our call will stop here. Our call will stop here. So that's how we can trace a tree, or we can use a recursive tree like that. Okay. So now you can see how much amount of time is required. How much amount of time is required to do that? You can see mainly our algorithm. What is our algorithm doing? This algorithm is printing a value and calling a functions. This is this algorithm is doing like that it is printing the value and bolo.
Sir,
4-time call.
Hmm?
4-time is called.
Our functions will call total 4 times, because this is calling 4 times. And how many times it is printing? This is printing 3 times. 1, 2, 3. This is printing 3 times. 3 times. So we can say from that if we take the value of n, if we take the value of n, then the number of calls will be n plus 1. And the number of times it will print the value, it will be n. Like that. Because in case of 3, we can see that there is printing the value as a 3. 3 times the value is printed and 4 times the call is generated. So in case of n, if we convert it towards n, then it will be n times the functions will be printed and n plus 1 time the call will be generated. Clear? Clear?
yes, sir.
Yes, sir.
Okay. So that's how our tracing tree works. Now, from there, we can say that now the amount of work done, we can say the amount of work done depends on the calls, depends on the number of calls, the amount of work done is calculated. Now, in this, our total number of calls is how many times? Our total number of calls is n plus 1. So the amount of work done depends on the call. The amount of work done depends on the call. So that's why we can say that our time function fn is equal to n plus 1. So time functions fn is equal to n plus 1 means it is the order of n. So our functions will be in the order of n, because if fn equal to n plus 1, I have seen in the previous classes also in the frequency counter that it will be on the order of n. Clear? So now that's how we can directly say that this functions is of order of n. Now this is performed using the tracing tree, or can say a recursive tree method. Now same functions can be converted into the recurrence relation method and it can be solved. So how it can be solved using the recurrence relation method? The result we get using the tracing tree or recursive tree, our time functions is in the order of n. Same as that, using the recurrence relation also, we will get our functions as a order of n. Now, one thing I have to mention here, that in the recurrence relation, it is basically totally mathematical calculation is required here. Okay, so this mathematical calculation should be clear to you. I will tell, but this mathematical calculation should be clear in front of you. So in recurrence relation, if we consider it recurrence relation, then in case of solving recurrence relation, we use as a Tn. Till now you have seen that we consider the time as a functions. For a time function, we used f of n. But here we could consider in recurrence relation the time as a t of n. Okay, so what this functions is doing? this functions is the total time is required, we can assume that the total time is required T of n, because solving this problem, we assume that total time is required T of n. Now, we omit the conditions checking. You can consider that. This can be considered. The amount of time required will be 1. You can consider it. But we have omitted it basically because the value which will be get, because the value will be we get plus 2, but we mainly what in case of this we consider it as a constant. Always, if it is 2, if it is 3,000, if it is 30,000, all are the constant values. And in case of constant values, we have seen in last that if we consider 1, then it will be that there is no problem for it. So I have omitted here for considering this, but you can take this value also, but it will not affect or in case of your recurrence relation, because in recurrence relation it will be like that as a constant, like used as a constant. So if it will be 2, if it will be 3,000, if it will be 3, that there is nothing mentioned. If as like that, it will be, we can consider it as a 1 because it is a constant. Always remember that if there is a constant value, we can write it as 1 also, because 3,000 all have a same meaning. It is constant. So for constant, we consider 1. So that's why I didn't take here the because amount of time I didn't take here, but you can take also that there is nothing mentioned here for that. Okay, so amount of time required, this is a condition, the condition is checked. So it is a simple statement and it will be required 1 time. But here I have not used this. I have not used in my program, didn't consider this value. So in case of this printing this statement is also for printing the statement. It requires 1 amount of time. And this is the recursive call. So this recursive call will take how much? It is n minus 1. So it will take t of n minus 1. T of n minus time, t of n minus 1 time, it will be required. Clear? So now, how
Sir,
we consider?
sir, it is applicable only for numerical value.
Only for numerical value, because it is a constant. We can consider it constant. I have said previous classes na, if we take 3,000, in case of if we get 3,000 or 3 or 4 or 40,000, both are for a constant. We can say it is a constant value. And that's why for a constant value, we can write 1 also. You write also, you can able to write 2 also, there is no problem. But our main motto is not about that. Our main motto is already finding the order of n, order of n square, like that. And in case of numerical value, it is considered as a constant. It's maybe 2, it's maybe 3,000, it's maybe 1, but it is a constant. And in case of constant, we consider 1. Okay.
Okay.
So that's why you can mention here. You can mention by taking 1 here also, because our amount of time required to this for this if condition, it will be 1. The time required will be 1. You can consider that also. But I am not considered here. So that's why it is, I have not mentioned here. You can mention here 1 also, because 1 amount of time is required. So here I have not mentioned here. I have mentioned that this value, for printing this value, it requires 1 unit of time. And for this is a recursive function. This is a recursive function. So n minus 1, that means it required t n minus 1. Okay. So now how to construct the recurrence relation? You can see now we construct the recurrence relation. Now you can see that how we construct the recurrence relation. Now we can say the time taken by this algorithm, which I have shown that the time taken by the algorithm is T of n. The total time taken by the whole algorithm is T of n. So our functions now, if we add this total, it will become, if we add this total, you can see this is became, this is our whole function. Tn is the value of total function. Tn is the value of total function. That's why it will be T of n. T of n. This is the total. So T of n is equal to T of n minus 1. T of n minus 1. So this will be so that's why here you can see this is mentioned as total time of the algorithm taken is Tn. So that's why here it is mentioned Tn equal to Tn minus 1 plus 1, because the whole algorithm takes Tn time, but the printing, for printing the value, it takes 1 unit of time, and it is the recursive function. This is the recursive call. So we can say Tn equal to Tn minus 1 plus 1. Clear? So now this function's Tn is equal to, it will be 1. We can consider it 1 when n value is 0. Now when n value is 0, it's only checking the conditions. But after that, nothing is performed because if condition fails. So for that reason, the checking is done. It is required 1 unit of time. So that's why if n value is 0, we can say the amount of time required is 1, because here no actions are performed. It only checking the value. It is only checking the value. So that's why it is mentioned as a 1. And if the value is greater than equal to 0, then the total amount of time is required Tn minus 1 plus 1. Till now it is clear how we can use that, how we can write that. Clear now? Clear till now?
Yes.
So if n value is 0, the loop, not loop, the if condition is not working. The if condition is not working, that means only the condition is checked, but nothing is performed. So it required 1 amount of time. And if the n value is greater than equal to 0, then it is the time required Tn equal to, the time required Tn equal to Tn minus 1 plus 1. So now, how to solve this problem? How to solve this problem? So for finding the solution of Tn, we have to first find the solution of this Tn minus 1. So if we get the value of Tn minus 1, then we can solve the Tn. This is the basically this is the method. So how we can do this? We can do this using substitution method. We can do this using substitution method. Now our Tn is equal to Tn minus 1 plus 1. So what will be our Tn minus 1? Now in case of n, we substitute the value of n minus 1. So Tn minus 1. Now what will be, it became T, in case of n, it will be n minus 1. So Tn minus 1 minus 1. That means Tn minus 2 plus 1. So our Tn minus 1 will be Tn minus 2 plus 1. So now it is substituted here. Now you can see it is substituted here. So what we will write here, you can see that we are writing substitute Tn minus 1 in this equation. Now it will become Tn minus 1 plus 2 plus 1. This is the constant value. So Tn minus 1 value is substituted. How? We can get this Tn minus 1 substitution value as a Tn minus 2 plus 1. So our Tn will become Tn equal to Tn minus 2 plus 2. Now I have to substitute this value. So Tn minus, for in case of n, we can write n minus 2. So when we write n minus 2, this will become Tn minus 2 minus 1 plus 1. So that's why you can see Tn minus 3 plus 1 plus 2, because this 2, that's 2 is, and we are substituting these values. So Tn minus 2, after substitution, the value will become Tn minus 2 equal to Tn minus 3 plus 1. So that's why this substitution occurred. And after this substitution, you can see, after this substitution, you can see it becomes, what it becomes? It becomes Tn equal to Tn minus 3 plus 3. So now we, after performing two steps, there is not required to perform all the steps, because after performing it will become then Tn minus 4 plus 4, then Tn minus 5 plus 5, like that. So for, we can say, directly say that if we continue for k times, then it will become Tn equal to Tn minus k plus k. This will be required, because if we perform these functions with k times, then it will become Tn equal to Tn minus k plus k. This total time will be required if we perform with the k times. Now our main motto is to make the functions, our main motto is to make it become 0, because if it is 0, then we can get the efficient solution, because it will be one amount of time will be required that time. So our main motto is to make this. So because at a time this, our recursion will be ended, it will be not continue till further. So at a time it will be ended, and that time the value will be 1. So our main motto is to make this element n minus k to 0, because if we perform, if t0, if tn, in case of n we make 0, then it will be t0 equal to 1. So for if n value is 0, it will become, it will take one amount of time to solve this problem, to finish this recursion. And for finishing this recursion, we should have the value 0, and if the value will be 0, then our time will taken by 1. So main motto is to finish this, and that's why for finishing this you have to make this element 0, otherwise it will be not finished, our recursion will be not finished. So that's why we assume n minus k equal to 0. So n minus k equal to 0 means after doing that n equal to k, if we solve this, it will become n equal to k. So after n equal to k, now we can say for k value it will be n. So in this case, we for k we use, because we get that k is equal to n, so substitute the value in the case of k. So tn equal to tn minus n plus 1, that is tn equal to t0 plus n, and our value will be tn equal to n plus 1. Now you see that what we get, the same number of calls, which we used using tracing tree, we are getting same number of calls. That is why it is tn equal to n plus 1, and it will be of the theta n. It will be order of theta n. So a program, an algorithm can be solved using tracing tree or recursive tree, and using that type of a recursive relation. So for recursive relation, you have to make the total time, and there will be two conditions. If the n value is 0, and another condition will be n greater than 0. In this condition, the value will be done, and after that, using substitution method, you can perform this operation and get the desired result. Clear? Till now it is clear?
Yes.
Baki look clear?
Yes, sir.
Huh?
Yes, sir. Yes, sir. Clear.
Okay. So that's how a recursion relation, a recursive call, a recurrence relation can be solved. And each each and every algorithm, we can solve it with recursive tree or tracing tree and recurrence relation. So this is in your syllabus, the recurrence relation. I have shown only one part. In next classes, I will also show how many parts. There are many types of how to solve this type of problems, because sometimes in the exam it is given, the recurrence relation is given, and you have to told that it try to solve it using recurrence relation. So the recurrence relation, basically one thing you have to in mind to solving the recurrence relation, I would suggest that you first try it with a tracing tree. If you first try it with a tracing tree, then the value will get, you will get easily. After the value you will get, you can then perform the recurrence relation. So in case of recurrence relation, you should keep in mind that you have to take two values. That two values is what? In case of n which is equal to 0 and in case of n greater than equal to 0. These two values will be, you for Tn there will be two values, and after that the n greater than 0, the value that is present in n greater than 0, it will be as a recurrence relation format, and you have to solve this recurrence relation using substitution method. Using substitution method, you can solve this recurrence relation, and after that solving this, you have to take in mind that why I give it 0. There is a thing that's why I have given 0, because your main aim is to stop your recursive relation, because there is not means that your recurrence relation will continue indefinite time. At a time it will be 0, means at a time it will be ended. That's why you have to make this element n minus k equal to 0. Yeah, or the element which you have get during the substitution and which element you will be get after the substitution, you have to make it 0. Otherwise, if you not make it 0, then your recurrence relation will be infinite time. So that's why your main aim will be to make it 0. And after making 0, you can solve it. Okay. So clear?
Yes, sir.
So in next
Yes, sir.
classes, next class, I will show some types of recurrence relation. This is the first type of recurrence relation. There is also some recurrence relation, but I will show in the class some recurrence relation, and you can able to solve this problem for any algorithm. Practice it for others. I will see in the next class. I will show you in the next class the other types of recurrence relation. Okay.